Good evening, everybody. So, I will be starting the session now. I'll just start with sharing my screen. Let me know if you can put it in the comments or you can just ask in the discussion forum if there are any questions. So welcome to the 9th live session of the NPTEL course, Essentials of Data Science with R Software, Probability and Statistical Inference. So we've had 8 sessions until now, right? This is the 9th one or for this 12-week course. And I would just like to mention before we start that the next session, which is supposed to be on the 29th of March, would actually be postponed to the 2nd of April, Tuesday. So on 2nd of April, which is 6 to 8 p.m. the Tuesday time slot. There's already one more session scheduled that day, but we'll have both of them simultaneously because there's something else planned. So I would not be able to take the class on the 29th. Okay, so let's start with what was discussed in this week. The first thing that was talked about is this bivariate normal distribution. So if you take a look at the univariate normal distribution that we have been seeing earlier, which is for the random variable x. Here, when you see this form, what has been known and what has been derived and proved, and we have also discussed this extensively in the previous sessions, is that when you see a random variable distributed in this format, in the exponent, the number that's subtracted from each of the random variables, that becomes the mu of that distribution or the mean of that distribution. And then this other variable here, which is sigma square and sigma here, so sigma indicates the standard deviation and sigma square indicates the variance. Now, taking cue from that, we extend this, and there could also be random variables. So the distribution of two random variables, x and y, if they follow this format, it stems from the original univariate normal distribution, because you can see it's very similar. It's a lot more complicated, but it's still on the similar lines. So once you see that, in that case also, the respective subtractions here, they are corresponding to the means of both the random variables x and y. And likewise, you have standard deviations or variances of both x and y as given by sigma x and sigma y here. Additionally, there's one more parameter, which is rho. And if you remember from the discussion a couple of weeks ago, this is the Pearson's correlation coefficient. All right. So this is there. Likewise, this can also be extended to more than two variables, which is going to be called as a multivariate normal distribution. And the way this is denoted is, so what you need basically is mu and sigma, right? So for mu, you can have a vector. It's going to be a one-dimensional vector, like either row vector or a column vector here. And on the other hand, all the sigma values, so they are standard deviations here. So it's going to be a P by P matrix, wherein P is the number of dimensions, number of random variables that we are interested in. And so the diagonal elements of the square matrix are going to be the respective sigma values. So for example, if it was only two variables, we would just have a 2 by 2 matrix, wherein sigma 1 is going to be corresponding to sigma x here, sigma 2 square is going to be corresponding to like sigma y square here, and the other two, so sigma 1 2 or sigma 2 1, it's the same thing, right? So that's going to be the covariance. All right, so this is about normal distribution. So we talked about the bivariate normal distribution, and from so we had seen last week that if you have a bivariate distribution, there are two things you can calculate from there. One is the marginal probabilities, right? So you are going to integrate. So in case of continuous variables as this, you integrate over one variable, whereas so you take up the whole range. You're no longer interested in how it varies. So again, if it's going to be a marginal probability of the random variable x, it becomes a normal distribution just in x, right? So everywhere you're going to substitute you're going to integrate wherever there is y here and y related parameters. And then so y goes out of the equation. So what you end up seeing here is a simple univariate normal distribution. Likewise, you can also calculate conditional probabilities. So here, let's say y given x, so which means um, some value of x is fixed and you're interested in what's the probability of y. So here also, this becomes a normal distribution, which is mostly in terms of y here, right? Because you're integrating over x and then you're fitting in that value. You'll integrate over y and then fit a value of x, so as to say in the denominator term, if you remember the how conditional probability is calculated, how we initially discussed that. So now so you can see the variable here is only x, right? So that you can fix depending on, the variable here is not x, but now this function is actually a univariate normal distribution. And then it is going to be in terms of y here. Y is only going to be the variable, and you can see that here this form, so the original mu y plus rho sigma y sigma x x minus mu x, this becomes the new mean of that normal distribution, and this thing right here becomes the standard deviation, or I should say the variance of that normal distribution, right? So all the four distributions here, they are now univariate normal distributions, though they have different means and different variances. But that new mean and new variance can be derived from the original set. So if you know what are the original values of mu and sigmas, you can calculate what the new values are going to be. And this is something which is also used a little bit in this week's assignment. And we'll just see a few sample questions just to give you an idea of how it's going to be done. So this was discussed. There are also some R commands that we'll discuss. So we'll do all of that towards the end of today's session. The other thing which was mostly talked about this week is something called sampling distributions for statistical inference. This is going to come a little bit more, a lot more in the upcoming classes actually. So what we've been doing until now, it's a random variable and you're looking at a certain function of that random variable. Likewise, here also we will be looking at some functions of the random variable, right? But now these functions that we'll look now, they are actually going to be useful in doing some statistical inference, which you would appreciate more in the upcoming classes. But this is to give you a little background on what these distributions are, right? So a statistic is it's a function of the random variable, and when you say it's a function, it's just some some value, something that you're changing of in some calculation on the random variable itself, right? So you can do something like, depending on how many random variables you have, you can take a sum of those, you can find the mean, or you can find the max, you can find the minimum, maximum, mean, variance, z value, which is like this, you subtract the mean and you divide by the standard deviation. So all of those, they are functions, right? So you're calculating some value from the random variable. That value is called a statistic. Okay. Now the distribution of that value, of those values, they are going to be called sampling distributions, and they have something which is called as the degrees of freedom, which we'll just see in the upcoming slides. And there are three types of distributions that were discussed this week: the chi-square distribution, the t distribution, and the f distribution. Okay. So we start off with the chi-distribution, the chi-square distribution, and this is what it looks like, right? This is the PMF, and this is how you denote it. So x tilde xn square. So square is this chi-square thing, and n here, the subscript here, is indicating something called the degrees of freedom, which again we'll see in a moment. But this is what it looks like. So you can see it's even more complicated than a normal distribution. Okay, so now, what does it mean when a random variable is following the chi-square distribution? So where does it come? What sort of random variables follow the chi-square distribution? So the first thing here is, so let's say you have many random variables, right? You have n different random variables, and these are all standard normals, right? So they're all going to look the same. So the mean for all of these is 0, the standard deviation or the variances for all of this is 1, right? So they're all distributed the same way, but they're independent random variables, right? You'd call them x1, x2, x3, xn. Now, what you can do, you can find the sum of their squares. So you square up all the random variables and then you sum them up. That sum, that is actually this sum of those squares. This has a chi-square distribution, and there's some additional parameter which is known as the degrees of freedom, and that depends on how many random variables you took initially. If you took n, then n is the degree of freedom. If you took m, then m is the degree of freedom. There's a slight more change. So if instead of those random variables being standard normals, if they're just normal distributions, so they do have a non-zero mu and a non-1 sigma square, then also you can take the sum of the squares, but now you take the sum of the squares of the z values, right? So what you're doing here is from each of the random variables, you are subtracting the mean, and you are dividing it by the standard deviation and you're squaring it up. Then this value now, so initially it was directly the sum of the squares, but now it's sum of the squares of this standard or this normalized and centralized value, and that has chi-square distribution again within degrees of freedom, right? And for any chi-square distribution, so initially you had n random variables, now you have a new random variable that has a chi-square distribution, and that random variable has mean as n and variance as 2n. Okay, so you can see here that the mean and variance, they now depend on how many random variables you took to begin with. All right. There are some more parameters, some more properties of the chi-square distribution, is that this is a non-symmetric distribution and all the values are on the right side. So there's nothing on the left. Okay, the value is 0. And we will just see all of these distributions in R. And since you've seen here that the shape, the mean, variance, everything, there's a very strong dependence on n, right? So that is the degrees of freedom. So how much can the curve vary? And at n greater than 5, the nature of the curve changes, which also we'll just see. There's one more property, which is like the additive property. So if you have two random variables, which they themselves are chi-square distributed with n and m degrees of freedom respectively, then the sum of those two random variables will also have a chi-square distribution. It's just now that the degree of freedom is the sum of the original 2 degrees of freedom. Also, so if you remember from one of the previous week's discussions, and we'll also see this at the end of today's class. So there is something called the sample variance and the population variance, and they're basically differing by what goes in the denominator. For the population variance, you divide it by n, and for sample variance, you divide that sum of squares of those differences by n minus 1, right? And the argument that's given behind this is that when you're taking a sample, you yourself are introducing some variance that needs to be accounted for. So which is why you now have to divide by a smaller number so that the variance is a little larger. Anyway, so if you make a new random variable, so like we discussed, mean, variance, all of these are also random variables, right? So if what you calculate, if you have sample variance and you divide it by the population variance and you multiply it by n minus 1, then that random variable also follows chi-square distribution. And this has degrees of freedom as n minus 1. Okay. Again, remember these properties, they can come up in questions, and there are a couple of questions based on this theme in this week's assignment also. Okay. Now, the last property here, and also you'll see for T and F distributions. So a lot of times, so especially in case of what we have been calculating until now was the CDF, right? So you are basically calculating the area of the shaded region up to a certain point, right? So normally, whatever the graph be, the CDF is going to be this part. right? So this is what the CDF typically denotes. But we would, in the upcoming lectures more so, we would be interested in the area to the right. So we'll also be interested in the area on the left, but a lot of times this right side, so greater than something, right? So your limits are going to be from a certain value up to infinity. When you're interested in that area, so the value of that integral when you're putting the limits, it's going to be called something called alpha, and we will see where this is being used in statistic, right? Because if you remember, we originally started. Hi, Vijay Lakshmi, can you hear me? Hello. Could you confirm if you can hear me? You can just put it in the chat. Okay, so I have actually started. Hi. Okay, great. So I did start the session. So maybe I'll just quickly go over it again because uh right, I waited for about 10-15 minutes, nobody joined. So for the sake of taking the session, I did start. So let me just quickly brief you through whatever I've talked about until now. So the first thing that was discussed in this week was the bivariate normal distribution. And this is sort of like an extension of the univariate normal distribution, which is this format. So again, there is no reason for you to remember the whole thing, but it's a good idea to get the hang of what this looks like. It will help if you can remember it. This was what you would probably have to remember, not the other ones that are coming up in the upcoming slides, but this one is easy and it's useful because you can identify based on the format what would be the value of the mean of x and the mean of y and the standard deviation of x and standard deviation of y and the value of rho, which is the correlation coefficient, right? And likewise, instead of bivariate, you can also have trivariate or quadrovariate and whatever nth variate normal distributions, or rather, we would say anything if you have like p random variables, sorry, p parameters. So multivariate where you have like p random variables here. So you can have, there are two things you would be using. Again, it's not, we're not going into so much details of the whole thing, but you would basically need, so as we have been defining normal distributions, it's based on the mean and the variances, right? So you need to have a list of all the means and you need to have a list of all the variances, which are going to be your diagonal elements of this covariance matrix. All right. And the other values that you see here, the non-diagonal elements, they're all covariances. And you know that covariances are actually symmetric, right? So covariance of 1 versus 2 and 2 versus 1, they're the same thing. So that's what this is about. And if you take a look at these two values, these like 2 into 2 matrix, this is what is this corresponding to. All right. Again, let me know if at any point of time you want me to repeat it. You can put it in the chat, you can unmute yourself. Okay. And then the other thing, which is also sort of a little bit complicated, but if you remember the concepts of marginal and conditional probabilities, what's being done here is that if you're integrating over one of the two variables and you're sort of doing away with that variable, you now just have one variable left. So it becomes a univariate distribution. And what happens is if you calculate, it's not just any univariate distribution, it is a normal distribution, the simple normal distribution that you know, right? So initially you had mu x and mu y's and sigma x square and sigma y square, but now you just have it in one of the variables when you're integrating over the other one. So this one's the marginal probability. And then you also have conditional probabilities that you can calculate. So once you do calculate conditional probabilities, so what's happening here is that, so if you remember conditional probabilities from the original formula, so if it says probability A given B, How do you calculate it? So let me just type this here. So this is, yeah. So probability, let's say it's A given B. So this is going to be equal to probability A intersection B divided by probability of B, right? So this is how we do it, right? And now instead, so when you're doing that, so basically that's what we'll be doing here. So the denominator is going to be just the one that's given. So x is equal to a particular value of x. That means you need to do away with the y, right? So denominator becomes when you're integrating over y, which is this one, and your numerator is going to become just your original distribution. So the original divided by this one. If you solve it, if you I mean, you don't need to do it, but then it's also going to become a univariate normal distribution. But now that univariate normal distribution would have this entire expression as the mean and this entire expression as its variance. Okay, so wherever you have mu here, you're going to plug that complicated phrase, and wherever you have sigma or sigma squared, you're going to put this thing. Does this make sense? If you could just give me a thumbs up or an okay, that would do.
Okay, ma'am.
All right. Okay. Thank you so much. So that was the first thing discussed. We'll also see a little bit of that in R. But the next thing that was discussed in this week was something called the statistic. It's a value that you calculate from a random variable, and that itself is also going to be a random variable. Okay. And it is basically an expression, right? You take square of something, you sum a few things up, you find mean of something, you calculate z values of something. So all of that, you're calculating it from some original values, right? So anything like that can be a statistic. And we would see some of those statistics here. And we will see that in all of these values, the number of original values you took, whether you took 5 or whether you took 30 or you took 100, that has some effect. So, and that is actually indicating how many random variables you took. Because a lot of times, so if you remember the original discussion of sample and population, so population is basically an infinite number of things, right? You can't do that. So you would instead like to take a sample. Now that sample can be just 5 individuals, that sample can be 100, it can be 1,000,000. So it depends. The more, the better. So which is why this degrees of freedom is nothing but sort of your sample size. And we will just see how this comes into the picture. It's going to be more explored in the upcoming weeks, where we will actually see how it's used for inferring some statistics between two groups. But before that, we just need to understand what some distributions are, what they mean, where do they come from. So we'll talk about 3 of them. So this is where I was when you joined the session. So, okay. All right. So we have talked about a few distributions, right? And we have mostly focused on, in terms of the continuous distributions, one of the most common ones is the normal distribution. And there are sort of 2 sorts of normal distributions we have discussed. One is the normal distribution, which is like, which has mean as mu and variance as sigma square. But there's something called the standard normal distribution, which has mean 0 and variance 1. So when you have n random variables and they're all independent and they're all standard normals, so they look exactly the same, right? The curve is exactly the same. Then if you sum their squares, so if you sum their squares, then that new that new distribution is going to follow the pattern that it's going to follow is going to be called a chi-square distribution and n degrees of freedom, and we'll see what that means. So this is how you depict it, right? It's going to be this format, and this is what it looks like. Okay, so a random variable can follow a chi-square distribution, and typically how you get that random variable is when you had n normal distributions and you summed up their squares. So that resulting random variable that has this.
Again, tell what is degrees of freedom?
Yes, okay,
Degrees
I will.
of freedom.
Okay. So now, so until now, so imagine n sort of these n random variables to be like basic random variables, okay? The following normal distributions. Now, you summed up 5 of them. Or in another example, you summed up 10 of them. So they're all going to look similar, but there's something differing them, which is basically how many samples you took. Did you take 5? Did you take 100? So depending on how many you took, the nature of the graph is going to be a little bit different. And that is what this n is here, right? So until now, so for example, you talk about normal distribution or any other discrete, whatever you've been taking until now, n was sort of never coming up in the picture, right? How many samples you took, that was not coming up in the picture. You only had mu and sigmas, for example, in normal distribution, right? But now here, this n, how many original samples were there? This is coming up in the picture, all right? So this is actually the normal distribution. Sorry, degrees of freedom. Okay, we will just see that in some graphs when we do a quick demo in R. Okay, but how many original random variables gave you this chi-square distribution is what n is denoting. Okay, does that make sense?
Yes, ma'am.
Okay, all right. So this is the example when you had standard normal distributions, but in case they were not standard normal, so you remember you can make any normal distribution into a standard normal if you subtract the mu and divide by sigma, right? So this value, it's called a Z value, centralized, normalized sort of a thing. So if you sum those squares, then that is going to become your normal, this chi-square distribution and n degrees of freedom. So you're basically converting your original random variables into standard normals. All right. So this is what the chi-square distribution is. And for every distribution, we normally talk about the mean and variance. So you can see here the mean and variance, they don't depend on the original mu and sigma anymore. They just depend on how many samples you took, right? So that degree of freedom, n or n in this case, that's the expectation, mean, and the variance here is going to be twice of that value. Okay. So again, here in this week, we are only talking about some new distributions and we'll just see their properties, but we are not going into how they're going to be used for sampling. That's going to come up in the upcoming weeks. Okay. So we'll just see all of these a little more in detail in R, but so this chi-square distribution, it's no longer symmetric and it's only there on the right side of the axis. So it's always greater than 0, if you remember this thing also. And the shape is depending on n, which we are calling as degrees of freedom. At n greater than 5, there's a lot of change in the shape of the curve. We'll see that as well in R. There's an additive property. So if you have two chi-square distributed random variables with n and m degrees of freedom, so if you sum those random variables, then you also get a third chi-square distributed random variable, and the degrees of freedom is now just the sum of the original degrees of freedom. Now this one, if you remember the discussion on sample and population variance, there are two different terms, right? So if you remember, when you're calculating variance, you're dividing it by n. That is the formula for the population variance. Instead, if you want to calculate sample variance, you need to divide it by n minus 1. So anyway, that's a discussion for some other time. But what you can see here, so variances are also random variables, right? So now sample variance divided by population variance into n minus 1. This is also a random variable and this also follows chi-square distribution. It's just that now this chi-square has degrees of freedom n minus 1. Okay. And so what I was telling here is that when you have a certain value of x that you're interested in, you may be interested in values, the area of the graph up to x or the area of the graph after x. When we talk about CDF, this is the area we look at, right? Lower value. But mostly for sampling distributions, so chi-square, f, and t, we would be more interested in the area on the right, so greater than a certain value. And that we are going to call as alpha. And again, how alpha is being used for statistical inference is going to come up in the later weeks. Okay, so this is what we talked about chi-square, right? So how does a random variable become, like, when you have a chi-square distributed random variable, where was it coming from? It was coming from some pre-existing random variables. And once you do have a chi-square distributed random variable, what's going to be the PMF? And what's going to be the expectation and mean? Expectation and variance, and there are some properties. So using a similar, like sort of on the same template, I'll be talking about the t distribution and then the f distribution. So we talked about how several standard normals give you chi-square distribution. Now, let's say you have two random variables. One of them is normal, the standard normal, and one of them is chi-square distributed. Then this thing, rather than doing that sum of squares, this expression, so the first one, which is a standard normal divided by y by n root, that follows TS, a distribution called student's t distribution, and that also has this n degrees of freedom. Okay, and this is what the PMF looks like. Here it's the whole range, less than 0, greater than 0. So you don't need to remember the PMF here. These are way too complicated formulas, so we don't want to go into that. And this is what the expectation and variance is going to be. So the expectation is 0. So the graph is central. It's centered at 0, and the variance is this value, right? N upon n minus 1. It's how it's been calculated. So if you can remember the means and variance, that will be nice. But you don't need to remember the PMF for sure. And this is how it's denoted. Okay, so x tilde Tn. So T standing for standard, less this T distribution, and N standing for the degrees of freedom, right? And then we look at some properties. So this is a symmetric distribution. This one looks very similar to a normal distribution. So let's say this was a normal distribution. The T distribution now is going to look something like this. Okay. So remember, the area under both the curves has to be 1. So for the red one, there's higher area on the sides and lesser in the middle. And for the blue one, it's higher in the middle and lesser in the sides. So, right, so this is the sort of color scheme that I'm using. So normal is this blue curve, and the red one here is the T distribution. All right, now this one also depends on n, right? So the shape is going to be slightly different. How much thick or thin it is, it depends on n. But what happens is, as you increase n, the tails become thinner and thinner, and the center becomes more and more. So after n is 30, both of these look very similar. So the blue one stays where it is. The red one starts squishing up. So the center is taller now and the sides are thinner now. Now there's one more. So as in the case for chi-square, we talked about sample and population variances. But now here, if you talk about sample variance and population mean, and this one right here is actually your sample mean. We'll just see that a little while again. So if it looks something like this, so you're taking the difference of population and sample means, you're multiplying it by root of n, and you're dividing it by the sample standard deviation, then that new random variable follows t distribution with degrees of freedom n minus 1. All right, and here also you can calculate the alpha value again from a certain value of x until infinity. Also, please let me know if I'm rushing, because just let me know if I need to slow down, if I need to explain anything else. Okay. Then the third thing that was discussed this week was the F distribution. So now if you instead have two chi-square distributions, and if you calculate this expression right here, then that new random variable is going to follow something called the F distribution. And it now has 2 degrees of freedom, right? One coming from each of the original chi-squares. And again, this is a very complicated formula, but it's okay. This one's also applicable only to things greater than 0. And this is what the expectation values are going to be. So now you remember, chi-squares need to have more degrees of freedom, right? So n here needs to be greater than 2. It cannot be even 2. It needs to be greater than that. All right. And because the denominator cannot be 0, right? And it can definitely not be negative because it's only applicable for greater than zeros, right? So there is a restriction on the value of n here. So n has to be greater than 4. Okay. So you need to have at least 5 samples taken for this chi-square. So it needs to have like a 5 degree of freedom minimum. Okay. That's the F distribution. And this one is also greater than 0. It's a little skewed to the right. We'll see in a while in R what it looks like. The shape again just depends on n. I will come to these 3 in a minute. Then the sample variances. So you now have 2 sample variants, right? For x and y. So those sample variances, if you take a ratio of those, then that has an F distribution with m-1 and n-1 standard deviation, degrees of freedom, right? And here also you can calculate an alpha value. Now, a little relation between F and T distribution is that if X has F distribution with M and N degrees of freedom, then 1 by X is going to have also an F distribution, but the random variables, but the degrees of freedom are going to be swapped. If X has an F distribution where M is 1, but N is non-1, then root of X is going to follow a T distribution with N degrees of freedom. And then you can reverse this whole thing, right? If X is Tn, the square of that is going to follow F distribution, right? So these two are just inverse of each other. Okay, so these are all properties that you can use. So if you know about distribution of one in one of these distributions, then something else can be derived from it. And we will see a couple of examples today. All right. The final couple of things that were talked about in this week, they are these population parameters. So basically the parameters you're interested in is mean and variance, right? You denote the population mean with mu and population variance with sigma square. Ideally, you don't know this, right? In the real world, you don't know this. There's no way for you to know this. So you instead calculate these things of the sample and you denote it with an x bar and an s square. And you would like to estimate the population parameters from the sample parameters. Okay. So, so now if there's a random variable, which is normally distributed, right? Then both its sample mean and sample variance, they're also random variables and they're all independent. So what you can do for the mean of the mean itself is a normally distributed random variable with its mean being mu and the variance being the original variance by n. Okay. And for the sample variance, you can't calculate the sample variance directly, but that divided by sigma square into n-1, as we saw a couple of slides back, that is now a chi-square distributed random variable with n-1 degrees of freedom. Okay, so for a sample, there are 2 parameters that you need to calculate, which is these 2. And both of these here, they follow some distributions, right? Because they themselves are random variables. So mean is a random variable which is normally distributed and variance is a random variable. The ratio of that, some sort of transformation of that follows chi-square distribution. All right. And then there was something called the convergence of these random variables, and especially in terms of probability, which was discussed this week. So what this expression here is telling you, so xn is your random variable, okay? Now you are interested in what's the probability that, so maybe you are interested in what are the chances that the value is very close to this x that you choose here. Okay, so this is what you're interested in. So what you want is, if you want to say two numbers are very close to each other, you can say that the difference is a very small value. Okay, does that make sense? Right? So if you're interested in A and B, you can say A is going to be really close to B, is going to be almost equal to B if the difference between the two is a very small value. Okay, and that small value here is talked about, is denoted as this epsilon. Okay, and epsilons are generally, epsilon symbol is generally used to denote small values. So you're taking this difference, okay, and you're taking the absolute value of the difference, because it doesn't matter if you've said A is greater than B or B is greater than A. Okay, so you're taking the difference between A and B, and you're saying that difference is greater than epsilon. So that's going to mean that these numbers are farther apart. That's not what you want, right? So you want this thing to not happen. The difference should not be greater than epsilon. So that difference is not going to be greater than epsilon means the probability of that happening is really low. So the probability is almost zero of this thing happening. Or you can say that the probability that the difference is smaller than epsilon, that's like almost one. We're almost sure this is happening. So if any of these conditions, they are the same thing. If any of these conditions are true, then you can say that your random variable is converging to a particular value. Now, if instead of x, you replace it with mu, okay, then we come up to something which is called the weak law of large numbers. So we have been talking about sample mean and sample variance and all of that, right? And basically, what is a good sample? This is something you might have heard in different contexts also. It's always good to have a large sample size. Nobody believes if you take just 3 samples and you say, okay, um, I looked at the weather for 3 days and it was always sunny, so I'm just going to say it's summers. But maybe if you increase it to a little bit, you take it for 10 days, and if it's still like that, you can say, oh, probably now I'll believe it more. And it's applicable for everything, right? COVID vaccines, COVID cases, some medicines, anything at all, right? A larger sample size is always good. So where is this coming from? Okay, so we talked about that we have sample means and sample variance with us, but we want to estimate population mean, for example. So we will again talk about two values here. One is this epsilon. So epsilon is just, it's also small value, but it can be anything greater than 0. And delta is a very small value. It's between 0 and 1 normally. And what you're saying is you're defining n as this value here, sigma squared divided by epsilon delta square. So now again, so if you remember, this is just an extrapolation of the previous thing we just saw. So see this one, right? Two values should be, so what we want, if you want to look at that convergence, so if we want the sample mean to be really close to the population mean, what we want is that this difference should be really small. It should be less than epsilon. And then this value right here, we want this to be as big as it can be. And probability can never be greater than 1. So what you want 1 minus delta to be roughly 1. When is 1 minus delta going to be 1? When delta is going to be a really small value. And if delta is a really small value, then n becomes a really large value, right? But that's what we're looking at, right? So at the cost, so if you don't have a large n, then this probability is going to be low. So your estimate is not going to be perfect. But if n is large, then this probability is also really close to 1. So you can say that your estimate is really nice. So this is a very strong result, I would say. All right. Okay. Do you have any questions still here? Before we go on to the practice questions, we'll quickly take a look at some of these commands in R. Okay. So let me know if there's anything you want me to explain in more detail. Otherwise, we'll just see these things. So for all the distributions that, okay, yeah. So for all the distributions that we've seen this week, if you remember from the previous weeks, there are 4 functions that we have always looked at. One is for the PMF, where you want to look at the nature of the curve itself. The other is for CDF, or the cumulative density function, where you're finding out the probability and its like actual value of the probability. The third one is the quantile. So you're looking at what's the value at which the random variable has the area, say 60% or 40% or something like that. And the last one is a random number generator. How many random numbers of a particular distribution do you want? Okay. All right. So the function for a bivariate normal or multivariate normal is not there in R by default. So if you remember some of the previous lectures, we had talked about how you can install a new package. So for installation, this is the command you're going to write. Install.packages bracket, and in double quotes, you write the name of the package. Here it is MVT norm, standing for multivariate normal as the package name. So for that, you need internet. Okay. So that installs some packages and it keeps it on your computer. So now you have that package on your computer. You now can use commands from that package. But every time you're opening R or you're opening RStudio, you might not need everything that's on your computer, right? So let's say today you worked in something, 1 year later, you may not need it, but you still have it on your computer. But it's not like every time you're opening R, you would need everything from every package. So even though it's on your computer, R does not load it into into this R session. So if you need something, you're going to tell R that please load it, please load the library. So the way you load the library is, again, you say write library, and in bracket you write the name of the same thing. Same name goes here and same name goes here. So this is to be done just once. And this thing right here, done every time R is opened, and like commands from this package are needed. If you don't need it, you obviously don't need it. Okay. So once you do that, you can also double check if you're using our studio. Here you have this packages pane. It's alphabetically arranged. You can scroll through. So you can see here, I have so many packages installed, but there is this tick mark in very few of them. So even though all of those other things are there on my laptop, but they're not loaded because every time I open R, I don't need all of this. Okay. So here you can see MVT, right? So MVT norm, it's here, but there's no tick mark. So if I want to find out some package, some function, so it's going to say could not find the function, right? But now what I do, if I run this, if I load the library, so I'm selecting it and I'm pressing Control Enter. If I'm doing that, and now if I write the name of the package, so it's a different error this time because I did not give it anything inside the bracket, but it was able to find the function. Okay. So again, yeah, this was just housekeeping information. So now if you want to find out what this does, so we'll just, so the basic, what it looks like is for any value of X and Y, what is the corresponding value of the distribution, the PMF at that value. And then you would need to give at least, so as many random variables, you need to give it the mean and the sigma values. Okay. Now I'll give you this command first. So let's say I have 2 random variables, X and Y. Okay. Now you see this thing I'm going to run. So this is the first column here is the values of X, And the second column here is the values of y. Okay, I have five values of both. So this is like my first point, this is the second point, third point, fourth, and fifth. Okay. And the mean, let's say the original distribution that is there, so mu x and mu y. So mu x is 1, mu y is 3. And what is this telling us actually here? This diag bracket C3, 5 is telling us that you make a diagonal matrix wherein you fill 3 and 4 in the diagonal and all the non-diagonal elements are going to be 0. Instead, you can also have a normal looking matrix, right? You don't need to make a diagonal matrix because this one's just here telling us that the covariances are 0, but they can be a different value as well. Okay. So anyway, this is what it needs to look like. So since I had two random variables here, my matrix that I give, the values, the PMF for whichever points I want to calculate, they need to be these two columns. And I need to give two values of means. And I need to be sure that at least the diagonal elements are what I want them to be. So once you run this whole thing, it runs and it gives you these five values. Okay. So corresponding to your five inputs of x and y, you got five values of the PMF at those points. So again, if you want to visualize this, you would ideally need a 3D look, right? So x-axis being your x variable, y-axis being your y-axis being your random variable y, and yeah, and the PMF being like the z-axis. You can also likewise do the CDF and the quantile. I would not be able to do the entire thing today, like, but this is exactly on the same lines as has been discussed in the previous weeks for the previous things. So it'll be a good practice to figure this out. But let me know if you're stuck. If you want me to show this, I will. Okay. And then likewise, you can also calculate random number generations. So again, how many random variables you want to calculate? That's n. What is the mean? So if you have like two values given here, then it would indirectly, I mean, it's indirectly going to tell the computer that you're looking for a bivariate distribution. And again, your sigma, it needs to be a 2 by 2 matrix in that case. Instead, if you would have given three values here, then sigma should be a 3 by 3 matrix. So the only thing is here as such, I'm giving it arbitrary values, right? I'm just giving it to show. So if I run this one right here, you can see that, okay, you got some random variables distributed, right? So this is the first x and y, and this is the second x and y. If you do, so if you run this last one right here, you'll get 10, 10 of each. Okay, 10 of x and corresponding 10 of y. Let's say if I'm running this third one here. So it says that it's some unexpected. Oh, sorry, no, not this. Yeah. So let's say this is also all right. But now if I run the third one here, yeah, okay. So the third one that I run here, it gives a warning, it runs it, but it says that sigma is numerically not positive definite. So there are also some restrictions on what the values can be, right? Because even though I'm giving it arbitrary values, internally those calculations have to make sense. Okay. They need to correspond to a graph that looks like that can actually fit. Okay. Like as a normal distribution. Okay. So these are the four functions for normal distribution. Likewise, we come up to the four functions of chi-square. For chi-square, the only parameter you are interested in is the value of df. Okay. So the way, if you want to look at what it looks like, so we'll be using the function curve. We'll be write DCHISQ, which stands for density chi-square. We'll write x and we'll write degree of freedom is 3. And if I run this is what it looks like. But by default, you can see it's the x-axis is only between 0 and 1. So I would add a parameter here. I'll write xlim that's equal to, let's say between 0 and 10. And if I do that, you can see this is what the curve looks like, right? So it's not symmetric. But this is what it looks like. Likewise, let's try some more values here. So if you see the degrees of freedom 1, it looked like a parabola. 2, also quite similar, but you see at 3, the nature of the graph changes. And then that continues for 3, 4, 5, and so on. Okay? There's an increase and a decrease. And then again, you can calculate CDF. So you would just want to calculate what point, up to what point are you interested in. So that's this first argument here. And if you do a lower tail, that's going to give you the CDF. If you do an upper tail, that's going to give you an alpha. Okay, again, where alpha is going to be used, we'll see next week. Quantiles, this is again telling you what value, at what value do you get 60% of your data. So if you run this, so it's gonna give you that for a degree of freedom 10 plot, at the value 10, you get 60% of the area covered. All right. And then of course you can do this random number generation as well. So 30 random numbers with 10 degree of freedom. This is what those numbers are. And it pretty much continues the same way for t-distribution, right? So this is what the t-distribution looks like. It's going to be centered at 0. And even though here it might look like it's all tapered, but it's a little different from a normal distribution. Okay, you can calculate the CDF, you can calculate quantiles, random number generations, and then we move on to the F distribution. Here, it's again same format, but now you need to give it two DF values. It's going to be as DF1 and DF2. Okay. There were two more functions that were talked about in this lecture, the density mean and the mean normal here. But since there are no questions associated with that in the assignment, and it was just a brief discussion, so I'm not sort of discussing it in this lecture today. But if you think this would be a good idea to discuss, let me know. We can discuss this in one of the upcoming sessions. But because this discussion would also then involve how a function is defined and how you call the function. So it would be beyond the scope of the problem session for now. So I'm skipping over that. Okay. All right. So we have had a discussion, we've seen an R. Now we will take a look at some practice questions so that you can appreciate how to solve these questions in the assignment. Okay. So it would be nice if you can work along with me. Okay. So how do you think we proceed with it, right? Okay. So you have a distribution, it looks something like this. The first question is, what are the means of random variables x and y? So would you like to tell me how we proceed with such questions? Okay. So what we're going to do here is that we're just going to simply compare it to this thing right here. Okay. So let's say I'll just take a screenshot. Is it this thing here? Okay. Okay. Right. So this is what a normal univariate distribution, bivariate distribution looks like, right? So if you compare it completely, you would be able to see that here, so the means here, they're actually this value 2, right? And the mean here for y is actually 4, right? We're simply seeing these values, mu x and mu y. And it shows up here as well. So that's fine. The second question, where you want to calculate the standard deviations, you can look at simply here. Okay, so the standard deviation, remember standard deviation is sigma, not sigma square. So standard deviation here is going to be
3,
3,
5.
3 and 5.
5.
Perfect. Great. All right. Then we also want to see the values of the expectation and variances of these conditional probabilities, right? So I'll not like explicitly tell you, it'll just take unnecessary time to write that down. But you can see this is what it looks like, right? So when it's x given y, now it's all in terms of okay, sorry. So this should be y. Yeah. Okay. So this is what the format is going to be. All right. So you can just plug in the values of like 3, 4, 5, whatever we have just calculated, and also row. Okay. So this is going to be the expectations or the mean. So the value before the comma is the expectations, and the value after the comma, they are your variances. Right? That's going to be okay, right? Because so there are a few questions like this in the assignment, if I'm not wrong. Okay. All right. So this is just simple comparison. Then you also have a lot of questions of this type. So wherein it's being asked, what is the value of this thing and how do you calculate it in R, right? So here you can see all of these, they are of the form greater than or less than. So it's going to use the Q function, right? Or the P function, sorry, I think, yeah. So it's going to be this one, PF, which is going to give you like probability up to a certain value or after a certain value. And in all of these cases, whether you have the chi-square or the t or the f distribution, the first value is going to be this value right here that you're looking at, okay? And then depending on whether it's chi or t, you're going to write the degree of freedom. So it's 15 in this case, 16 or 15 in this case, and you'll have 2 degrees of freedom in case of the f distribution. And then when it's this less than equal to symbol, the lower tail parameter has to be true. And when it's the greater than symbol, then the lower tail parameter has to be false. So lower tail means up to. So this less than thing, up to that value. And lower tail false means after that value, right? So you can have the respective R formulas. And when you solve those, this is the values you're going to get, okay? I will add this up, or maybe I can just add this up here. Okay, so this is what these values are going to be. All right. So, but this is straightforward. It stems from the same the if you write the command, this is exactly what it's going to give you. All right. Now there are two more questions which are slightly non-direct questions. So I would like to take a moment and discuss these. I think one or two of these is there in the assignment. I don't know if both of them are, but okay. But let's try and see this. So an experimenter is attempting to locate a target in 3D space, and they have 3 coordinate errors. All right. So 3 errors are there, and these errors, they are random variables. They are independent normal random variables with a mean mu and a standard deviation 3. Okay. So what's the probability that the distance between the point chosen and the target, it exceeds 4 meters? So now you can see from here that we are talking about 3 random variables which have a normal distribution, and we want to calculate a probability which is going to be some combination of those random variables, okay? So now just to give you a hint, this is what you're looking at, okay? Something like the second point here. So instead of n, you have 3 random variables. They have a normal distribution, right? It's not a standard normal. It's not 0, 1. It's something else. So the sum of the squares of the corresponding z values will have an x distribution, a chi-square distribution. Okay. So how do we go for it? So first of all, what we are asked is that the probability, what's the probability that the distance, let's call it d, it exceeds 4. Okay, this is what we want to know. This is one thing. Now, the other thing that we sort of also alongside can do is that let's call these three random variables as, let's call them as x and y and z. Okay. So we know that x minus its mu, which is 0, divided by, so it's sigma, so that's 3, this square plus y minus 0 divided by 3 square plus z minus 0 by 3, right? So we're calculating the z values for all of this. So this random variable, this is going to have a chi-square, I should denote it like this. So this is chi-square with 3 degrees of freedom, right? This is 1, 2, and 3. This is what we know, okay? So it's basically going to be x square plus y square plus z square divided by 9. So this random variable, we know how it behaves. So what's the way to convert this distance in terms of these errors? Now there's a concept called the Euclidean distance, okay? Where what we're going to do is, so let's say if d is greater than 4, then definitely d square is going to be greater than 16. So whenever you have an equation, whether it's an equal to sign or whether it's a greater than or less than sign, you can do the same thing on both sides. I'm taking the square of both sides. So what I know, actually, Euclidean distance is actually this thing. Sum of 3 coordinates gives you a distance, the square of that distance. Okay, so this formula is what I'm going to use for my benefit here. So what I'm going to write, so I can also divide the whole thing by 9, right? So do you see this thing coming up here? So now what I'm going to do is divide both the sides by 9 as well. Okay, now this one right here, probability, is actually a chi-square distribution, right? 16 by 9. I want to calculate, sorry, yeah, I want to calculate this thing. So what's the value for a chi-square distribution with 3 degrees of freedom? That it's going to be greater than 16 by 9. So I'm going to use the p chi-square thing here. Okay, PCHISQ in brackets in R. The first value I'll write 16 by 9, comma, degree of freedom is 3. And lower tail false, because I'm interested in the greater than value. And that's just going to give me the probability here. I don't think I have noted what the answer is, but we can, yeah, so I think this is what this is. Okay, so it's, so this one is question number 5. So if I run this thing here, it's going to give me 0.62. So 0.62 is the probability that the distance between the point chosen and the target, it's more than 4 meters, right? So yeah, this is the analogy that we are using. All right. So does this make sense? Okay. If this is fine, then we move on to, I think, the last question for today. So now the time it takes to fill a medicine bottle, that's normally distributed with a mean 10 and a standard deviation 3. Now, if a sample has like 20 such jobs to fill the bottle, what is the probability that the sample variance is going to exceed 12? All right. So, so here what we are going to do, so we have a normal distribution that's 10 comma 9, right? Because so sigma is equal to 3, which means sigma square is equal to 9 and mu is equal to 10, right? And now we want to calculate the probability that the sample variance, which is S square, that is greater than 12. Okay. Now again, we will go back to, okay, and there's one more thing, N is 20 here. So let's go back and see what we are going to use. So if you remember this thing, right? So N minus 1, S square by sigma square, that follows a chi-square distribution with n-1 degrees of freedom. Okay, so what I can do is, so let me divide both the sides by sigma square, right? So 12 divided by 9, and then let me multiply this by n-1. So n is 20, so n-1 is going to be 19 into 12 divided by 9, right? So I can simplify 19 into 12 by 9. This is going to be 3, this is going to be 4. You can solve this up. 12 into 19. Yeah, so you can solve this, whatever the value comes up. And then, so this is going to follow chi-square and with 19 degrees of freedom. So again, we're going to use the same formula, PCHSQ, degrees of freedom being 19. And the value that we're looking at is this one. So 19 into 4 by 3. And then you'll get your value. All right. So the last two questions they're on similar lines. So the original random variables, they're now transformed into a chi-square distribution with different degrees of freedom. Okay. Yeah, so this is what we're going to use here. All right. So before we end the session, are there any questions from assignment 8 that you would like me to talk about? Because so there are basic groups of questions in this assignment. So the first 8 questions were based on this entry right here. Okay. The patients, whether they're elder or children or young, and depending on the dosage that they were given. So the first part is obviously you reading in these values, and then you making these contingency tables. And depending on what the contingency table says, you can do some minor calculations, some percentages and some numbers. And then, so this is how the first 8 questions are going. Okay. The next one here is the joint probabilities. So for this expression, and we, I think, had calculated, I think, the same value or a very similar value in the last week's assignment, in the last week's problem session. Okay, so I think we had, yeah, exactly. It was these 3 values that we had calculated. So it's sort of already discussed, and the distribution is also like basic integration is also given here, but we had talked about this in detail in the last week. So in case you want to look at it, you can check that video or those slides. It's all there. This is also like
Eighth question, so madam. Eighth question.
8th question. This one. Which of the following statements is correct? This one.
Yes, yes.
So what's the confusion in this one?
This one, we thought the number of elder patients who are given the small dosage is more than the number of younger patients who are given large and medium dosages.
Okay. So here it says, so 200 is the total number of patients, right? So total there were 200 patients. And number of elder who are given small dosage. So elder small dosage is 21, right? So 24, this thing. And young patients who are given large and medium, so 16 plus 16, so that's 32. So 24 is less than
So under
32.
represent addition, summation.
Okay. Oh, I see. So see, there's no case of and, right? There's no and case here, as in there's no intersection case here. I understand where the confusion is coming from, but you don't have this intersection information, right?
Yes, madam.
So which is why we are summing this up. Although I can still take this up with the other instructors who are making up the questions and grading. I am only responsible for the live sessions, but okay, I will ask them. I've noted down assignment 8, question 8.
Why not? Why not A, madam? Option A is also correct. No, see 24. 24 is greater when comparing to young large and young median.
Yeah. So, but you're splitting. You're keeping large and medium separate. So
Yes.
I understand where this confusion is. I will take this up with the other instructor. That there is confusion in the question. Meanwhile, what you can also do is, so there's the discussion forum of the as NPTEL course, right? When you log
Yes,
into the
madam.
course,
My question, my answer is right or wrong, madam? That is
no,
B put.
so B is correct, right? B is the right answer.
Only B is correct.
Yes, yes.
So and is nothing but here the and represent. We
I
have to add
understand.
16, 16,
I
16.
understand. I understand why the confusion is, but here the and means that we're talking about either of the cases. But it's a good point that you raised, that here and is not meaning what we've been understanding what and means, right? In probability.
Yes, madam.
Okay,
Yes.
I will let them know.
No, eighth, this is eighth assignment. In the
Hmm.
sixth assignment, I think
Mhm.
one option is not given in the
Yes,
assignment.
yes, yes. So I think if you
But
check
it
the
shows a new option in the answer script.
solution, huh? I
Uh,
remember. Yeah.
um,
So if you
uh,
check the discussion forum, this has already been addressed, and they say that
uh,
that question will not
but
be
our
evaluated.
mark is reduced, madam. Marks are reduced.
Huh, so it will get corrected. It might take some time to reflect on the NPTEL page. Please check again
Yes,
after a
madam.
week.
Another
But still,
another thing, one more option is not there.
haha,
Eight,
I
that one is
remember.
also.
I remember.
Yeah, yeah, yeah.
Just check
Mm.
after a week or so. It takes a little time to grade once if something's
See,
here and there.
yes, madam. We request, please go through what the students get the assignment and answer script. Please compare with that, madam.
Yeah, yeah. So
Because
I am not responsible
uh,
for setting up the questions. It's a different
yeah,
teaching assign
yeah,
as
anyway,
teaching.
this is only way to be convey directly.
Yes, yes, of course. So I will. So
Uh,
it's good that you've told me. I will also convey this further.
yeah, thank you,
Although
madam.
it will be even more effective if you just post it on the discussion forum alongside. So it's going to be there in record that you have said this. If two, three
Yeah,
people say
yeah.
this, then they'll be more careful. Right?
Yes,
That's the
madam.
only thing
Yes,
I
madam.
can recommend at the moment. All right,
Yes,
fine.
madam. Yes, madam. Thank you, madam.
Is there any other question from this assignment you want me to discuss?
Yes, madam. Another question, I think, 15th question,
15th.
15th,
Okay.
no, 15th, no, madam, 15th is right. Uh, one more question, yes, madam.
So this is
8,
11 integration.
9, 10, R software, by using R software only. Got
Our
one result,
software,
but
so it's going to be 13, 14, one of these.
yeah, 13. Yeah, this number, madam. This
This
number,
number.
we got A, madam, option A.
Okay, so now if you remember
Mm.
again, covariance here in R is using n minus 1 as the denominator, but we want to calculate with n. So we multiply it by n minus 1 and we divide by n. Simple maths. If you remember, this was discussed last week. So
Yes,
I'll just explain it to you again. So what R calculates, let's say it's calculating, let's say you got this value. So there's this numerator and it's calculating this thing. So this is what R is giving you something like 7.35. Okay. What you want is this value. This is what you want. So what you can do is from this value, from n into n minus 1, you multiply it by n minus 1 and you divide by n. So these two get cancelled. So you get this thing back. So 7.35, which is the covariance, that you multiply by 199 and you divide by 200. N was 200, right? In that question. Right? So the covariance, you multiply that by 199 and divide by 200. So you'll get this value. This was mentioned in last week, and this is a slightly trick question and trick solutions also. Okay.
yes, madam.
All right.
Yes.
Okay. So that's it then. All right. And just to mention something, the next week's so anyway, so this deadline for this week's assignment is going to be the coming Wednesday. And next Friday, I would not be able to take a session. Instead, the session that I'll take is going to be on Tuesday. So on Tuesday, most likely there are going to be 2 sessions simultaneously. But anyway, you will still get an update for that, whatever it is. I will let you know in the meantime. Okay. You'll get an email from the NPTEL team, but most likely I would not be taking a session on Friday. It'll be on Tuesday. All
Yes,
right.
madam. Thank
Okay.
you, madam.
All right. Thank you so much for attending today's session, and I'll see you within the next session then. Bye-bye. Good night.
Please convey our grievance, madam.
Say that again.
Please convey our grievances.
Oh, that's okay. Yeah. Of course. I will tell all of these things.
Thank you, madam.
Okay.
Thank you.
Thank you so much. Bye-bye.
Bye.